Hello. Hello.
Good afternoon, madam.
Good afternoon, Dr. Srivastava.
Madam, we will wait for 5 minutes as the participants will be joining so that we can start up after 5 minutes.
Okay. So can I share screen and see if that's working now?
Yes, madam. I just give you the co-host.
Okay. Can you see it now?
Yes, madam. We can see your screen.
డౌన్లోడ్ చూపిస్తాం.
చేస్తే డౌన్లోడా ఏడ చూపిస్తుంది డౌన్లోడ్ అని
స్క్రీన్ షాట్ పంపించినావు
డౌన్లోడ్ అని లేదు. Good afternoon, everyone. I welcome everyone to this fourth day of this 1 week online National FDP on fundamental mathematics. This program basically celebrates birth anniversary of Mariam Mirza Khani, the field medalist. Now I call upon B. Maheshwari to introduce today's speaker, Professor Rukmini De Madam.
Yes, ma'am. Good afternoon, everyone. I, B. Maheshwari, faculty member of Mathematics and Statistics Department, RBVRR Women's College. Welcome you all once again to day 4 of 1 week National Level Faculty Development Program organized by Mathematics and Statistics Department, RBVRR Women's College. I take this opportunity to introduce our speaker of this session, Rukmini De ma'am. Ma'am has completed her MSc in Mathematics in 1992 at IIT Kanpur. Ma'am has been a great student from September 1992 to June 1998 and being instructor from September 1998 to 2001. Ma'am has worked as postdoctoral research at ISI, Kolkata, and also worked as a faculty at Harish Chandra Research Institute from October 2001 to 2003. Ma'am has worked as a faculty in IIT Kanpur, and now ma'am presently working in International Research for Theoretical Science, Bangalore. Ma'am's current research interest in geometry and in mathematical physics. Now I invite Rukmini De ma'am to take over the session. Welcome you, ma'am.
Thank you very much. My heartfelt thanks to all the organizers, and I am really honored to be part of this celebration of the birth anniversary of Professor Mariam Mirza Khani. Can everyone see the screen and can everyone hear me? Hello?
Yes, ma'am. Yes, ma'am.
Okay, great. So I'll be talking about minimal and maximal surfaces, some common properties. So initially I'll be only focusing on minimal surfaces and I'll be talking about some of the properties, and then finally the maximal surfaces, and I'll tell you the what are the common properties we have found so far. So there will be a lot of pictures in this talk, and all these images are from publicly available domains in the website. So surfaces, you know, surfaces, you must have heard about surfaces like the sphere, the torus, the double torus, and so on. They are topologically characterized by their genus. These are compact orientable Riemann surfaces. And the ones which I will talk about, they may have some punctures and also they can have some boundaries. I won't always be talking about compact surfaces. In fact, most of the time, no. So what is geometry of surfaces? When we talk about geometry of surfaces, we talk of lengths of curves on surfaces, area of the surface, Gaussian curvature, mean curvature, etc. In this sense, sphere and ellipsoids, though topologically equivalent, are very different. Why? The sphere, for example, is totally symmetric, while the ellipsoid is not totally symmetric, right? So when we talk about surfaces in R3, we talk about parameterizing them locally. Okay. So locally, supposing UV is a parameter and X is a map from UV, a region in R2 to R3. Okay. So X, this capital bold X, has 3 coordinates: X of UV, Y of UV, and Z of UV. And UV belong to a domain in R2. So basically, though there are 3 coordinates, there are only 2 independent parameters, so that the surfaces, it generates a surface locally. Okay. A surface in R3 can be locally parameterized by like this. Well, U and V vary in a domain in R2. One example, let's take the helicoid. Z is equal to tan inverse Y by X. It can be locally parameterized in many ways. Away from 0, 0, you can parameterize it at U, V, tan inverse V by U. Okay, that's one characterization. Or you can parameterize it in R theta coordinates as R cosine theta, R sine theta, theta. Okay, again, once again, X is not equal to 0, Y is not equal to, I mean, it's the origin, X is equal to Y, 0, Y is equal to 0 is not there in the domain. Okay, so then this is a helicoid. Now I can introduce a novel parameterization. I can complexify U and V in the sense zeta is equal to U plus IV, such that X of UV is small x zeta zeta bar, Y of zeta zeta bar, Z of zeta zeta bar, where X is given by imaginary part of a holomorphic function, that is minus half imaginary zeta plus 1 over zeta. Y is given by half real part of zeta minus 1 over zeta, and Z is given by minus pi by 2 imaginary part of ln zeta. One can show that these two surfaces are actually, this is also the helicoid. Okay. So this is a novel parameterization in terms of one complex variable. And in that sense, you see that all the coordinates are harmonic because they are real or imaginary part of holomorphic functions of zeta. And this representation fails for zeta is equal to 0. So how does the helicoid look like? Well, it looks like a spiral staircase like this. Okay. So just leave out the origin, the axis, the z-axis passing through the origin, you leave that out. And then this one spirals around that. Okay. So now normal and tangent to a regular surface at a point. So now if there is a regular surface, regular means the tangent plane can be defined. So there is a plane which touches it at point P. Okay. And normal is the normal to that point. So if X of UV is a regular surface parameterized by 2 parameters, X of UV is XUV, YUV, ZUV locally, then the partial derivative of X with respect to U is a vector in R3, and XV is again a vector in R3. You evaluate them at P. Okay. There are 2 vectors in R3 and they are linearly independent because it's a regular surface. And they span the tangent space at P. So basically, XU is nothing but small xu, small yu, small zu, where by that I mean you take partial derivatives with respect to u. Similarly, xv, you take partial derivative with respect to v, and you evaluate everything at p, and then you get the basis vectors of the tangent space. And what about the normal? The normal is the cross product, right? The normal is the cross product. So xu cross xv divided by norm of xu normal. Norm of xu cross xv is the unit normal at p. Okay, this evaluated at p is the unit normal at p. Okay. So what are minimal surfaces? Minimal surfaces, we'll be talking about locally area minimizing surfaces called minimal surfaces, which appear in nature as idealized soap films. For example, if you have a wireframe and if you dip it in soap solution, you will find that there are many of these surfaces which appear, right? Which span the curve. Similarly, if you take two rings, dip it in soap solution, you will get this kind of a surface. And supposing there's no effect of gravity and all, then they will be called minimal surfaces. Okay. So they are idealized soap films. They have the property that the mean curvature at every point is 0. They are locally area minimizing, which means locally mean curvature is locally, what I mean is at every point, the mean curvature must be 0. This one can show. Okay, so they are actually 0 mean curvature surfaces in Euclidean 3 space. So if K1 and K2 are the two principal curvatures, then K1 plus K2 is 0. That means K1 is minus of K2. If K1 and K2 are not 0 themselves, then the two principal lines of curvature actually curve into opposite directions. So it has a saddle-like structure at every point. If K1 and K2 is 0 at that point, then it's called an umbilical point. And there the Gaussian curvature is 0. Everywhere else, the Gaussian curvature is negative because Gaussian curvature is K1 times K2. Since K1 is minus K2, you will have it's K minus K1 squared. So if K1 is not 0, you will have that's negative. So Gaussian curvature is either 0 or negative on a minimal surface. But I must say a word of caution. Soap bubbles are spherical and not minimal surfaces since they have non-zero mean curvature at every point. They fall under the category of constant mean curvature surfaces, which can be approached through the theory of integrable systems. Let's take a look at some examples of minimal surfaces. So this is the helicoid and this is the catenoid. The helicoid is what I showed earlier. Catenoid also we will show a representation soon. And we will also show that they are actually related in some sense. There's a whole family of minimal surfaces which take you from one to the other. So that is, so in a sense, they are conjugate minimal surfaces. Then the NA surface, two NA surfaces, two kinds of NA surfaces. One looks like a potato chips, one looks like a self-intersecting, this kind of a beautiful surface. Then these are the shark surfaces. This is shark's second surface, which has a lot of these tunnel-like structures. And this is the shark's first surface. I've drawn it vertically. This is the genus 1 Costa surface, immersion of a torus with 3 punctures. This actually has genus 1 with 3 punctures. And it's self-intersecting. And you can see the 3 punctures have become 3 ends. This one, and this one, the 3 ends. Okay. This is the Riemann staircase. And this is the genus 1 and multiple genus helicoid. Triply periodic minimal surface. So these are all pictures I got from the internet. They are publicly available. And yeah, so Now, what is the Plato's problem for the layperson? Given a small closed wireframe, if you dip it in soap solution, is there any soap film spanning it? And if so, how many? So Jesse Douglas gave the answer to the mathematical formulation of this question, and he said yes. And subsequently, this has become an active field of research. And you know, Jesse Douglas got the very first Fields Medal, which was ever given. So he got that for this work, solving the Plato's problem. Okay, now you can ask how many such minimal surfaces span a given curve. And this has been studied by Tromba and other people using bifurcation theory, catastrophe theory, and so on. Okay. So, for example, already you can see if you have a Mobius curve, okay, if you dip it in soap solution, there are two kinds of surfaces which appear, this type and this type. And this type also, depending on the thickness of your curve, depending on the shape of your curve, there could be so many possibilities, right? And one can analyze the stability and so on. So, okay, now, remember I said that minimal surfaces are zero mean curvature surfaces. Now, harmonicity of coordinates in isothermal parameters. Locally, if the minimal surface can be written as graph of a function of two variables, that means it's supposing of the form x, y, phi of x, y, then mean curvature 0 implies the surface is phi, the minimal surface, the height function phi follows the following nonlinear equation: 1 plus phi x squared phi y minus 2 phi x phi y plus 1 plus phi y squared phi x is equal to 0. Okay. However, for minimal surfaces, there exist certain parameters called isothermal or conformal parameters. This, in fact, exists for all smooth surfaces and also for minimal surfaces. And so x of uv, y of uv, z of uv are conformal parameters. And what are conformal parameters? Conformal parameters as such, I have written it in red here. Mod of xu equals to mod of xv, and xu xv norm, xu and xv are orthogonal. That means xu xv inner product is 0. Okay. So in these coordinates, a miracle happens and the minimal surface equation becomes just harmonicity of coordinates. X of uv x, Laplacian of uv x equals to 0, coordinate wise. So this small x is harmonic, this small y is harmonic, z is harmonic. Okay, harmonicity of the coordinates. That's what, remember, we saw in helicoid also. Each coordinate was harmonic function. So this is a harmonic function of uv, each of them. And harmonicity of the coordinates makes it possible to relate the theory of minimal surfaces to complex analysis. Real and imaginary parts of holomorphic functions are harmonic. Okay. And also from here, one can conclude that complete minimal surfaces cannot be compact. Okay. They cannot be compact. So sphere without any holes or anything or punctures, just the sphere itself cannot be a minimal surface, cannot be realized as a minimal surface. Similarly, the torus just by itself cannot be realized as a minimal surface, but torus with 3 punctures, I showed you, torus with 3 punctures can be shown as a minimal surface, can be immersed in R3 as a minimal surface. Any questions? Okay, you can ask questions in the end of the talk. Weierstrass, but in the middle also you can stop me anytime. Okay. The Weierstrass-Enneper representation of minimal surfaces. So zeta is u plus iv and zeta bar is u minus iv. Then for every non-planar minimal surface, x is zeta, x as a function of zeta. Zeta bar, a simply zeta belongs to omega, a simply connected domain in C. There is a holomorphic function f and a meromorphic function g in omega, f, g not identically 0, such that Fg squared is holomorphic in omega. And then this immersion, x of zeta zeta bar, x0 plus real part of zeta 0 to zeta half f into 1 minus g squared d omega. Similarly, y x naught plus real part of zeta naught to zeta I by 2 f 1 plus g squared d omega. And phi, which is phi naught, real part of zeta naught to zeta f g d omega. dw, I'm calling it w, sorry, this coordinates I'm calling it w. So the dummy coordinate. So this gives you a minimal surface. So this is very powerful. As soon as you can find your own favorite f and g, which satisfies just this simple thing, f is holomorphic, g is meromorphic, fg not identically 0, and fg squared is holomorphic. Then you can construct a minimal surface. Okay. So, and all minimal surfaces are given like this. So both ways, you take your favorite f and g which satisfy those conditions, you write like this is going to be a minimal surface, and the other way. Every minimal surface can be represented like this. So this is called the Weierstrass-Enneper representation. Okay. And sometimes you can write it even simpler. In a neighborhood of a non-umbilical point, any minimal surface can be represented in terms of one non-vanishing meromorphic function r omega, such that x is of the form real part of zeta naught zeta 1 minus w squared rw dw. Y is y naught plus real part of zeta naught to zeta I 1 plus w squared rw dw. Phi is phi naught plus real part of zeta naught to zeta 2w rw dw. Okay. So for example, now you can construct your minimal surfaces according to values of r you choose. So r is equal to 1 corresponds to the Enneper surface. Like remember the potato chips and the surface next to it. Similarly, r is equal to k by 2w squared corresponds to the catenoid. R is equal to ik by 2w squared k real corresponds to the helicoid. Similarly, r is equal to k e to the I alpha divided by 2w squared correspond to the general helicoid, which I'll show in a minute. Then 2 by 1 minus w to the 4 corresponds to one of the Shark surfaces. That is the first Shark surface, the tunnel-like one which I showed you. And then r is equal to this complicated thing corresponds to the other Shark surface, the red one I showed you. Okay. I'll show them again, so don't worry if you don't remember. So r is equal to 1 minus w to the minus 4 leads to the Henneberg minimal surface, and r is equal to this corresponds to another type of minimal surfaces, and a is equal to 1, b is equal to 0 corresponds to the Catalan surface. Okay. So all this is available in Nietzsche's book on lectures in minimal surface. And Weierstrass-Enneper representation is also available in many books. I'll talk about it later. I have also derived it using hodographic coordinates. Okay, so this is the Shark's first surface, second surface, and this is the Shark's first surface. Okay, and so
అక్కడ పెట్టండి ఆయన మీరు వెళ్ళేటప్పుడు మళ్ళీ తీసుకెళ్ళాలి మీరు అక్కడ బయట పెట్టండి చెప్తా ఒకసారి ఇవ్వండి సారీ ఒకసారి ఇవ్వండి.
Hello. So the Weierstrass-Enneper representation of the catenoid. So phi is cos h inverse square root of x squared plus y squared. That corresponds to the catenoid. And if you use this formula, that r is equal to k by 2w squared and perform that integral in the r representation, then you get the catenoid looks like this. X is half real part of zeta plus 1 over zeta. Y is half imaginary part of zeta minus 1 over zeta. And phi is minus real part of ln zeta. The representation breaks down at zeta is equal to 0. And representation for the helicoid, again, if you take r is equal to I by 2w squared, then you get x, y, z to be these, and that's a representation of the helicoid. This is what I was talking about in the initial slide. Okay. And there's an isometry between helicoid and catenoid. How do we see that? Well, if x is the capital X, which is x1, y1, z1 is a minimal surface, and y is x2, y2, z2 is another minimal surface, then they are called, and both of them are in the same isothermal coordinates zeta1 and zeta2, then x and y are harmonic conjugates of each other component wise. Supposing x1 is harmonic conjugate of x2, y1 is harmonic conjugate of y2, and z1 is harmonic conjugate of z2, then x and y are called harmonic conjugates of each other. In that case, cosine theta x plus sine theta y will be a minimal surface again. Okay. And cosine theta x, so, and this is the case for catenoid and the helicoid. If x is the helicoid and y is the catenoid, then there is a isometry, there is a conjugacy between each of the coordinates. x1 is conjugate to x2, y1 is conjugate to y2, z1 is conjugate to z2. And then again, cosine theta xh plus sine theta yc is again a minimal surface for theta, each theta. And in fact, it's an isometric deformation. So this is the helicoid, and then you can have a family of deformations to catenoid, and this is the picture. And at every stage, there's a minimal surface corresponding to theta values. Okay. So that is the isometric deformation. And then the last topic I want to talk about is geometrical representation of an identity of Euler-Ramanujan. So if you have, there's a consequence of, so there is a Euler-Ramanujan identity, tan inverse tan h y cot x is summation k is equal to minus infinity to infinity tan inverse y divided by x plus k pi. Now the left hand side is the height function of the first surface, that red one I said. And the right hand side is the sum of height functions of shifted helicoids. So tan inverse y by x is the height function of the helicoid. Remember, x, y, tan inverse y by x was the helicoid. And now you're shifting x to x plus k pi. And summing over k goes from 1 to infinity. Okay. So basically this red surface can be obtained if you sum infinite sum of these shifted helicoids. This was discovered and used by a condensed matter physicist and his collaborators, Randall Camion in UPenn. And we used it to derive some more identities. Okay. So there is also possibility of finite decomposition. So this means what? That a minimal surface height function you're decomposing in terms of height function of other minimal surfaces, which is surprising because the minimal surface equation was very nonlinear. You cannot add up the height functions of two minimal surfaces and expect to get a minimal surface. But in this case, that's what's happening. An infinite sum on the right hand side of minimal surfaces adding up to a minimal surface, height function of a minimal surface. Okay. So that's very surprising. And finite sums are also possible, but in this case, it is possible to decompose the height functions into scaled and translated versions of itself. So z of xy, where I have ln cosine y by cosine x. This is the height function of the shark's second minimal surface. Z is equal to ln cosine y by cosine x, the tunnel-like one. Okay. So then z of xy equal to sum over m goes from 0 to n minus 1, x divided by n, z of x divided by n minus cm, y divided by n minus cn, where n is an integer and cm is 2m minus n plus 1 divided by 2n into pi. Okay. So that this means if you take the height function of the Shark second minimal surface, if you scale the coordinates and translate them, and then you take a sum, then you will get back the height function of the Shark's second minimal surface again. So, but of course, the translation has to be done with this particular constant, 2m minus n plus 1 divided by 2n into pi. And again, this particular one is proved using Euler-Ramanujan identity. So ln of cosine x plus a by cosine a is this quantity where x and a are complex and a is not an odd multiple of pi by 2. If you can take ln on both sides, then this is the sum. And using this, one can prove the identity. So basically, sometimes minimal surfaces can be written as translated and scaled versions of the same type, finite sums. So interpolation of two real analytic curves by a minimal surface. Given two real analytic curves close enough, there is a connected minimal surface joining both of them. This follows from Douglas's work. We show it using Schwarz-Bjorling problem and inverse function theorem in infinite dimensional setting. Now I promised you I'll talk about a little different type of surfaces. They're maximal surfaces in Lorentz-Minskowski space. So what is Lorentz-Minskowski space? Lorentz-Minskowski space is R3 dx squared plus dy squared minus dz squared is the metric. So in Euclidean space, the metric is dx squared plus dy squared plus dz squared. Here, the metric is dx squared plus dy squared minus dz squared. So it's a Lorentzian matrix. And if x comma y comma f of xy is a graph of a function locally, then the zero mean curvature equation is 1 minus fx squared f by y plus 2 fx fy fxy plus 1 minus fy squared fxx equals to 0. So it's a little modification, little variant of the minimal surface equation. For the minimal surface, this was a plus, this was a minus, this was a plus. Here, this is minus here, plus and minus. Okay. And now you will also have to put some conditions. Fx squared plus fy squared is less than 1. So that the surface becomes space-like. So in Lorentz-Minskowski space, there are space-like, time-like, and light-like surfaces. So these surfaces, the maximal surfaces are space-like. And the zero mean curvature equation in Lorentz-Minskowski space is this. And this is known as the maximal surface equation. And again, there'll be a Weierstrass-Enneper representation. If the Gauss map is 1, 1, it can be written in terms of one meromorphic function m omega. And x zeta can be written like this, y zeta can be written like this. So again, you see it is very similar to the minimal surface except the signs. For the minimal surface, the first one, x zeta was x0 real part of zeta 0 zeta r of 1 minus w squared d omega, dw. Here, it is x0 plus real part of zeta 0 to zeta integral mw 1 plus w squared dw. Similarly, this one and this one, they are just difference of signs here. So once again, you can choose your m's suitably to get different kinds of maximal surfaces. Different examples can be chosen, can be constructed using different values of m. For example, space-like elliptic catenoid. X of uv is cosine u, sine hv, sine u, sine hv, v. Space-like parabolic catenoid. X of uv is v plus v cubed by 3 minus u squared v, 2uv, v minus v cubed by 3 plus u squared v. And space-like hyperbolic catenoid, V sine HU, sine V cosine HU. And there are also corresponding time-like catenoids, space-like catenoids, time-like helicoids. Okay. So some of examples are hyperelliptic catenoid is this, parabolic catenoid, hyperbolic catenoid. So these are the possibilities. These are the pictures. And these maximal surfaces have many properties analogous to minimal surfaces. So I had shown that Weierstrass-Enneper representation can be for minimal surfaces can be obtained using hodographic coordinates. So my student Rahul, ex-student Rahul Kumar Singh, he showed it for maximal surfaces. So of course the actual original proof of Weierstrass-Enneper representation is different, but it can also be given a very PDE kind of a proof using hodographic coordinates. Then they have relation to complex Born-Infeld solitons and some identities, again the Euler-Ramanujan identities and the Weierstrass-Enneper representations give you new identities, plethora of new identities. For maximal surfaces, of course, the identities are slightly different nature, but you can get those. And then studying the problem of interpolation of two arbitrary real space-like real analytic curves by maximal surfaces. And one can do various other analogous questions can be answered. For example, given a Riemann surface of arbitrary genus and K punctures, can you construct a corresponding maximal surface? Can you construct a corresponding minimal surface in R3, which is an immersion of this surface? This topologically, it's a Riemann surface of genus G and K punctures. Can you realize it as a minimal surface or a maximal surface in R3? And yes, the answers are yes. And a lot of very famous mathematicians have worked on that and given solutions. So there are all these analogous questions you can ask. And parts of my talk are based on so very elementary books. Dokarmo's book on differential geometry of curves and surfaces, Osserman's book on survey of minimal surfaces, Bjerkes, Hildebrand, Koskeuster, and Walrab, minimal surfaces, Nietzsche's book, Lectures on Minimal Surfaces, Withham's book on linear and nonlinear waves, Andrews Byrne book on Ramanujan's notebooks, Lopez's book on Lopez's lectures on differential geometry of curves and surfaces in Lorentz-Minskowski space, and me and my collaborators, me and my ex-students, Pradeep Kumar and Rahul Kumar Singh, we have written a lot of papers in these directions. Weierstrass-Enneper representation using hodographic coordinates on a minimal surface, one parameter family of solitons from minimal surfaces, Ramanujan's identities, minimal surfaces and solitons, Born-Infeld solitons, maximal surfaces, Ramanujan identities, existence of maximal surfaces containing even curve and special singularity, interpolation by maximal and minimal surfaces, and finally, finite decompositions of height functions of minimal, maximal surfaces, Born-Infeld soliton, time-like minimal surfaces. Okay, so that's all I wanted to say today. Thank you. And the floor is open to questions. Anybody can ask. I like it if a lot of people ask a lot of questions. So please ask. So let me keep the basic books picture on. So if anybody wants to watch.
Golconda Crossroads, under Risalagada, Kalkampu. Masjid ఇంకా లోపల డౌన్.
Hello. Any questions? Hello, I'm done. Can you hear me?
Yes, madam, we can hear you.
Okay. So,
Any participants, if you want to ask any questions, you can answer. Otherwise, you can post in the chat boxes.
okay, looks like there are no questions.
Thank you, madam, for readily accepting our invite in spite of our busy schedule and for enlightening us by your lecture, madam.
Thank you
Thank
so
you.
much. Okay. So, one quick question. So, this recording won't be in the YouTube, right?
Yeah, it will be there in the YouTube, madam.
Oh,
If you want, I just send you the YouTube link, madam.
I didn't really want it on the YouTube, but okay. Somebody has asked a question. Yeah, there are many YouTube videos for minimal surfaces. You can see there are many YouTube videos for minimal surfaces. Just type in, you will get hundreds of them. Okay, then.
Please accept the appreciation certificate, madam.
Thank you so much. Thank you. So, how do I accept that?
I just send in it to your mail, madam.
Okay, sure. Thank you so much.
Thank you, madam. Now I call upon B. Maheshwari to propose formal vote of thanks.
Thank you, Shweta ma'am. It is my pleasure to present vote of thanks on behalf of Department of Mathematics and Statistics, RBVRR Women's College. At the outset, I thank our resource person, Rukmini De ma'am, for accepting our invitation and delivering a wonderful lecture on minimal and maximal surfaces and their common properties, and learning geometry of surfaces and examples of minimal surfaces using different theories. Maximal surfaces in Lorentz, Minskowski space, and their examples. Thank you so much, ma'am.
Thank you so much for inviting me.
We are thankful to our Honorable Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mutyam Reddy sir, and our Secretary Correspondent, RBVRR College, Professor G. Sudarshan Reddy sir, for their continuous encouragement in organizing program. I would like to thank our Principal, Dr. Achyuta Devi ma'am, for her support. A special thanks to Shweta Srivastava ma'am for organizing 1 week National Faculty Development Program. Our heartfelt thanks to all the participants. Thank you, ma'am.
Thank you. So should I just leave the meeting?
You, madam.
Huh?
You, madam.
Hello?
Yes, ma'am.
Yeah. Okay, then I'll leave the meeting.
Okay, madam. Thank you very
so
much, madam.
It was an honor to speak to you all. Thank you.
Good afternoon, sir. Good afternoon, Hassan, sir. Can you hear me?
Yeah, I can hear you. Yes. You can hear me too?
Yes, sir. We can hear you. Now I welcome Lakshmi Prasanna to introduce today's speaker, Professor Yasin Hassan, sir.
Thank you, ma'am. It's my privilege to introduce today's speaker, Professor Syed Nazimul Hassan, sir. He is the head Department of Mathematics and was Dean, School of Sciences, Maulana Azad National Urdu University. He also holds the position of Dean, Research and Consultancy at Maulana Azad National Urdu University. Before joining Maulana Azad National Urdu University, he was head Department of Astronomy, Usmania University, Hyderabad, and Director, Japal Rangapur Observatories. He completed his MSc and MPhil at the University of Hyderabad and PhD at the Moscow State University, Moscow, Russia. He was recipient of National Merit Scholarship, University Merit Scholarship for his master's programs and Ministry of Human Resource Development, MHRD, Government of India Scholarship for doctoral studies. His research interests are celestial mechanics and dynamical astronomy. He has published his research in national and international journals and has more than 25 years of teaching experience. He is actively involved in Olympiads, public outreach and science popularization programs for children and adults. Thank you, sir. Thank you for giving this opportunity. Please take over the session, sir.
Thank you. Thank you for the introduction. And I would like to thank the organizers of this workshop for having given me this opportunity to talk to you. I'll be talking on the women of orbital mechanics. So before I get down to the main topic of my talk, since we are celebrating the life and works of Maryam Mirza Khani, just a slide as a tribute to her. Maryam Mirza Khani was an Iranian born mathematician. She was a professor at the Stanford University. Her research topics included Euler theory, hyperbolic geometry, ergodic theory, and symplectic geometry. In 2005, she was honored in Popular Science 4th Annual Brilliant 10, in which she was acknowledged as one of the top 10 young minds who have pursued the fields in innovative directions. In 2014, Mirza Khani was honored with the most prestigious award which is given to mathematicians, which is the Fields Medal. She was the first lady mathematician to receive this honor, and in fact, she's the only one to this date. The award committee cited her work in dynamics and geometry of Riemannian surfaces and the moduli spaces. So this brilliant lady has visited Hyderabad, and she's an inspiration to a lot of mathematicians, not just women. One thing I would like to get across to all the lady participants here, all the girl students here, that it's not that women are not good at maths. They are as brilliant, as good as men are. But the only reason why only one lady has ever got Fields Medal is because of the biases our society holds. So from a very long time, women were denied to even get admission into universities. Then they were denied admissions to study certain areas. And there is a bias which still goes on even in this 21st century, where people feel that mathematics, astronomy, astrophysics, physics is not for women. Women should do literature, they should do biology and other sciences, things like. It's not that biology is any little or literature is anything bad to work in, but they should not be a bias. It should not be with an idea that women cannot do it. It's not true. We just had a brilliant speaker just before me who gave an excellent talk on minimal surfaces. And here we have Mariam Mirzakhani, and I would be talking about some more women who have contributed tremendously in orbital mechanics. So the reason for me for choosing orbital mechanics is also because it is something which is very relevant in the 21st century and in the Indian context. And it is a subject which is neglected. It is not taught in India at all. And the reason why I say it's very relevant and important is India has an indigenous space program, and ISRO is one of the most successful government organizations in India and has been doing tremendously well. Indians have built their own methods of launching satellites and reaching all the way up to Mars and at a very low cost. We have a very successful program, and behind this ISRO, behind every successful launch, there are mathematicians who work out the equations, put in numbers, and find out the orbits which are required. They have to calculate the time at which the launch has to be made. And it's all mathematics and physics. And since celestial mechanics is not taught in India, I felt that this should be introduced to the young girls who are present here. So, what is orbital mechanics? The very word, it's made up of two words. Mechanics is the study of particles or a system of particles or a system of particles in motion. And orbital comes from the word orbit. An orbit is a regular repeating path that one object in space takes around another. Alternatively, to define it in a more specific, in a better way, I would give you the second definition, which says an orbit is the gravitationally curved path of one object around a point or another body. Yeah, this is from Wikipedia, and it's very interesting. You see that the orbit needn't be around another body. Generally, when we talk about orbit of moon, orbit of sun, and so on, we are talking about orbits of these celestial bodies, about some other objects. But we can have orbits even around points where there's nothing sitting there at all. And I'm going to talk about those points as we proceed ahead. So we are familiar with these orbits of planets around the sun, the natural satellites around planets, which are often called the moons of those planets, and orbits of the artificial satellites. The reason why I have colored this orbits of highlighted artificial satellites is because when I'm going to talk about the orbital mechanics, I would be talking about the mechanics of the artificial satellites which we have launched and which are orbiting our Earth or the moon or the sun and so on, and the various probes which we have. So we are mostly interested when we talk about orbital mechanics, though the rules of the game are learned from orbits of these natural celestial objects, but we apply these rules to artificial satellites and we get them to do things which we require these satellites to do. So here's an example of an orbit. You have a big mass and a small one in the red. And the center of mass is shown right at the beginning. And this blue big object will go around the center of mass. And the red one again goes around the common center of mass. So really speaking, when these things are orbiting, they are not orbiting anything they are orbiting just a imaginary point, which is the center of mass. So at the heart of finding, how do we find orbits and so on, at the heart of it lies this mathematics problem, which is called the two-body problem. So here we take two bodies. You have one mass here, and we have the other one here, and they have certain velocities, they have certain masses, and we need to predict their motion. And how do we write the equations of motion? We use Newton's second law of motion, which says force is proportional to acceleration. If the greater the acceleration implies there's a greater force, or the greater the force, you have a greater acceleration, right? So Newton's second law, which says force is proportional to acceleration, gives us these equations of motion. In fact, I will just stop here and share the whiteboard to show you how we acquire equations of motion. So if you have any mass and you know its position, right? So always when you talk about motion, it has to be with respect to some reference point. So arbitrarily, I am taking a point O as my reference point, and I would like to write the equations of motion of this. And one of the ways you can do it is we can use vector notation, and using this, I give a unit vector, which gives the position, which is the position vector of mass m, right? So if the vector is given by, is denoted by r, then its velocity is given by r dot, which is basically dr by dt, right? And acceleration is its second time derivative. So you take the second derivative and you take the second time derivative of this, and this is what your acceleration is. So if you want to study the motion of this mass m, you write the mass and the acceleration, and you have to see what is the force which is acting on it, right? So depending on what are the forces acting on this particular body, you may have different forces acting on it, F1, F2, F3, and so on. And vectorially, you add all these forces and you get the resultant force, which is the resultant of all these forces. And you substitute that force here, and you just solve these differential equations. So in the case of the two-body problem, suppose by two bodies, I mean I have two masses. I have mass m1 and I have another mass m2. I have the position vector of the first one given by, say, r1. Yeah, with respect to some arbitrary origin, I have r1, and I have the position vector of the other one, which is r2. And I want to write the equation of motion of both these masses. So equation of motion of m1 is m1 r1 double dot, which is the acceleration, is equals to the force which is acting on m1. And what is the force? The force is the attractive force. We know we invoke Newton's gravitational law, and Newton's gravitational law says that the force, whenever there are two bodies, there is a force between them, which is proportional to the product of the masses and inversely proportional to the square of the distance, right? And it is in this direction, right? This direction. And what is this direction? It is R2 minus R1, okay? And since mathematicians are lazy people, they always find convenient notations, and that's what I will do. I will write R1, R2 as this vector, and the unit vector I denoted with a cap, R21, okay? And this essentially is R R21 divided by the modulus of R21. Yeah, that is the only the right. So every vector has two components. Any vector has two components. One is this its magnitude, and the other one is its direction. Right. So this is the force acting. So your M1 into R1 double dot is equals to G, yeah, and your proportionality, you get rid of this proportionality and make it a equality by putting the universal gravitational constant. And mind you, this force is the magnitude of the force. And this is the magnitude. And if you want to see the force as a vector quantity, then you'll have to give the direction in which it is acting. Okay. So you have G M1 M2 by R21 by R21 square, right? So if I multiply by R21 on top and I multiply below R21, what will I get? I will make space here. And what I finally get is equal to G M1 M2 by R21 vector. It's a unit vector, and the magnitude of it put together, you get back R21 divided by R21 cube, because you have a square here and you have 1 here, so that becomes a cube. Okay. So yeah, our equation of motion is M1 R1 double dot equal to G M1 M2 by R21 cube R21. Okay. But what you have seen in my equations is a negative sign here. It's because I've replaced 2 1 by 1 2, right? I've just written this 1 2 1 2. That's why I get a minus here, right? So basically R12 is minus of R21. Yeah. R21 is vector in this direction and R12 is a vector in the opposite direction. So this is our equation of motion of first particle with respect to the center of mass. And in the same way, you can get the second equation, M2 R2 double dot is equals to minus G M1 M2 by R21 this time by R21 cube. Okay. So these are the two equations of motion which I have written there. And I go back to my presentation. So these are the two equations. M1 R1 double dot is minus G M1 M2 by R1 cube. R12 it should be. Yeah, I should have 1 2 and 2 1. Similarly, 1 2 and 2 1 here. Okay. Yeah, so we have to solve this. So writing equations of motion is extremely simple, but when you come down to solving it, it becomes a bit difficult. So one way of solving this two-body problem, which is solvable, is by I subtract these two equations and I get the equation of relative motion, that is motion of one with respect to the other one. So if I go back to my whiteboard again, what I would like to say is you have this M1 R1 double dot is minus G M1 M2 by R12 cube R12 and M2 R2 double dot equal to minus G M1 M2 by R21 cube R21. Okay. And you'll notice there's M1 here and M1 here which cancel out. You are left with only M2 here. And here M2 and M2 cancels out. So we are left with only this here. So we get this. And yeah, these are the equations. And when I subtract these two, I get R, either I do R2 double dot minus R1, right? From this equation, from equation 2, I am subtracting equation 1, and I get G M1 plus M2 by R21 cube by R21, right? And this is R21 double dot, yeah, acceleration, minus G M1 plus M2 by R21 cube R21. So basically, we have written the equation of motion of mass 2 with respect to mass m. We have shifted the origin from an arbitrary location to this. Our m1 has become the point of reference. So now we are, so instead of writing 1, 2, 2, 1, I can write R21 as R itself. So this equation becomes R double dot equal to minus G M1 plus M2 R by R cube. Okay. And to make it look even more elegant, I write R1 to, since G M1 plus M2 is a constant. This is a constant, this is a constant, this is a constant. So I write mu as G M1 plus M2, right? So I write this as this plus mu R by R cube equal to 0. So this is our equations of motion of one body with respect to the other. And we could have done the same thing. I could have subtracted 2 from 1, and I would have got exactly the same kind of an equation, which would be the equation of motion of M1 with respect to M2. Okay, so this gives me these equations, which I have below here, which gives me the equation of relative motion. And this can be solved also not very directly. We take a substitution where you take R as 1 by U, and to get rid of this denominator, which can become a 0. And then if you solve it with little mathematics, you can solve, and you get this solution, right? So the solution to the two-body problem is this this expression, and what does this denote? This denotes a conic section. That is, if you take E as 0, then this R equal to P, a constant, gives you a circle. If E lies between 0 and 1, we get an ellipse. If eccentricity is equal to 1, you get a parabola. And when eccentricity is greater than 1, you get a hyperbola. So the beauty of the whole thing is that if you have two bodies and one body is moving about the other, the only possible paths are the sections of a cone. These are called the conic sections, because if you take a cone and take cross sections, if you intersect a cone by a plane, yeah, if you take a cone, and if you intersect it by a plane, if I intersect it by a plane which is absolutely perpendicular to this axis, central axis, yeah, if I intersect it by a plane of this kind, then I get a circle here, right? If I intersect it above, I get smaller circles. If I keep going down, I get bigger and bigger circles. If I intersect it by a plane at an angle, then what I get is I get an ellipse. And when I intersect it by a plane which is parallel to this edge, if I intersect it by this, then I get a parabola. And when I incline it more, I get a hyperbola, right? So these conic sections were studied by mathematicians 2000 years before for the beauty of studying it. And when people started studying the motion of planets around the sun, all the works of these great masters became very essential. And it was that all these planets, they either take a circular path, an elliptical path, a parabolic path, or a hyperbolic path. So the objects which come towards the sun in a parabola, they have one interaction and they go away to infinity. So is the case with hyperbola. If they are in elliptical paths or a circular path, then they go keep orbiting that central body again and again. Okay, so this is our ellipse, and these ellipses are more interesting for us because circle is a special case of an ellipse, and all the planets, they are going around the sun, not in circular, but elliptical orbits, right? So that's what even Kepler had said. You have the sun at one of the foci, and the planets go around in elliptical orbits. So these are the orbits, and eccentricity gives you how ellipse deviates from a circle, how the major axis and minor axis are different. Each a square minus b square root of it by a gives you the eccentricity. And when your a is equal to b, then like you notice here, it will become, b would also become a squared, and this will become x squared plus y squared equals to a squared, which is the equation of a circle of radius a. Okay. And similarly, we can work out and see that it spans equal areas and equal intervals of time. So by using those equations and a little bit of calculus, we can prove all the Kepler's laws, and we see how true he was. And we can also show that the square of the period of these orbits is proportional to the cube of the semi-major axis. Okay. So this is an animation of two equally massed bodies which are going around their common center of mass in elliptical orbits. So there are times when they come close and the times they go together, and they would go on and on forever this way. So similarly, you can have many such possibilities, and here these are. And when you want to study the motion of one body with respect to the other one, say this could be the sun at the center. Suppose we have Earth at the center, and we are looking at a satellite which is going around us. So there are certain orbital elements which defines the orbit of an orbiting object perfectly, and these are the inclination. There is the reference plane, and the inclination of the orbital plane to that is given by I. Your omega, so the point of intersection of these planes, which it makes with the x axis, is the omega. And then you have longitude of the ascending node, which is small omega. E, which is the eccentricity, and A is the semi-major axis. So A, E, I, small and big omega, these are the 6 orbital elements which perfectly fix up a certain orbit of a object. Yeah, so it's the semi-major axis, the eccentricity, the inclination, the longitude of the ascending node, and the argument of the periaxis. These are the 1, 2, 3, 4, 5 of them. And tau, it gives the time of the periastrant passage. That is the time at which it is crossing the closest point to the central body, right? That's the tau. So these 6 elements define the position of any orbiting body perfectly in space. So the question is, why just 2 bodies? Why can't we have n bodies? So if you take n masses and you do the same thing, you can write equations of motion in the same way. And this is very easy to write. So this gives you the equations of motion of the n body problem. So our solar system essentially is not a two-body system, but you have the sun, and it has 8 planets, and there are many comets, there are many asteroids, there are moons of various planets. So this is a many-body problem. It's an n-body problem. So technically speaking, if you are looking at our solar system, you should take this summation, I going from 1 to n with this. Okay, so these equations are exactly the same way as we have got earlier. But important thing one has to note is when your n is equals to 2, then you can solve it completely. You've got a solution, and the solution is this solution. But when the number of bodies go from more than n, more than 2, that is, it becomes 3 and more, then there is no general solution for the 3-body problem. So in the summation, when I change n to 3, I get the n equations of motion of the 3-body problem, and you cannot find a general solution to this. But it was shown by Poincaré that there are many partial or periodic particular solutions. So the nature of the 2-body problem is it has a solution. They are the Keplerian orbits, but the 3-body problem has no general closed form solutions, but there are many particular solutions. So you can use numerical techniques, or you can use computers to find these solutions to this. So here they are animation of 2. Here there are 3 bodies which are going in this figure of 8, and they move in such a way that they maintain the symmetry of the problem, and they would go on and on without colliding with each other also. So one way of looking at our problem is, see, when we are trying to put satellites into orbits, why do we do that? We put satellites which study the weather, and they can tell us if there are any cyclones approaching, or right? They have satellite images. There are satellites, communication satellites, on which our telephones work, our televisions work. We have innumerable defense satellites which protect our boundaries from intrusion by enemies and so on. So we can monitor. So there are innumerable ones. And if you look at our sun, earth, and a satellite system, here the satellite has such a small mass that it cannot perturb the motion of the other 2 masses, right? So this brings us to the restricted 3-body problem. So we are imposing a restriction on the 3-body problem, where we say one of the masses is infinitesimally small. It's extremely small. And if you do that, your equations of motion come down to this. And if I multiply each equation by the first equation by x dot, the second by y dot, and the third by z dot, and add them up, I get something called the Jacobian, right? I get a relationship which says x dot square plus y dot square plus z dot square equal to 2 omega minus c. And what is this omega? Omega is this function, which is basically the potential. So here again, we are writing the equations of motion, but we are writing the equations of motion. Instead of writing force, we are writing it as the differential of a potential. Omega is the potential, and omega x means dou omega by dou x, partial differential of omega with respect to x. And these are the equations. And if you plot these curves by giving different values for c, you get these equal potential curves. So you get regions where motion is not possible, or motions are right. So what it says is, for a given value of c, suppose I get this curve, either the motion is possible outside this, or it is possible inside this circle, or inside this circle. So a body close to this will go around this, or a body close to this will go around this, or the body should be far enough to go around both the masses, right? So you get these zero velocity curves, and you also get certain points here, L1, L2, L3, L4, and L5. These are called the Lagrangian points, or they are called the equilibrium points, or they are called the libration points. These are very interesting points. These are the points where the gravitational forces and the Coriolis forces of the whole system, they cancel each other. So these, one thing I missed out to tell you is I have written these equations of motion in a rotating frame where I always keep the Earth and the Sun on the x-axis. And as the Earth moves around the Sun, the x-axis also keeps moving. So we are taking a rotating frame, and hence you get this term, which gives you the Coriolis force. So the point at the center is called the L1 Lagrangian point. And you can understand here that there can be a point where the forces, there's a gravitational pull on the left because of one mass, and there's a pull on the other side due to the other mass. So there should be a location where the two forces cancel each other, right? So this is a Lagrangian point. Similarly, there is another point here, and you would wonder that both the bodies will be pulling this object. If I place a satellite here, this is also pulling it in this direction, towards the left, while this body is also pulling it in both directions. So why do I call it a equilibrium point? It is because we are taking a rotating frame, and there is a Coriolis force and the centrifugal force which acts on this, and that negates these gravitational pulls of these two. So similarly, we have this L3 point, and these are the L4 and L5 points. So there are points here where there's a gravitation pull by one body in this direction, another in the other direction, and there's a centrifugal force acting outwards, which cancel each other. So these are the points which are equilibrium points, where the forces, the net force is zero. So obviously, the first thing which can come to your mind is, can I place a space station here so that the gravitational force is not there and it will always remain there, and we can monitor, the Sun sitting here or the Earth sitting here? And yes, that is what is being done. And we have various satellites which are placed on different Lagrangian points. And we'll come to this as we proceed ahead. Okay, so for this restricted three-body problem, by taking different initial conditions, by giving different velocities, different initial position, different mass ratios, I could plot all these beautiful different periodic orbits. So there are innumerably many periodic orbits. These have been done on a computer using Earth, Moon, and a satellite system, where the satellite is a restricted object, right? So orbits can be of different shapes, which you see. It's a star shape, circular one, oval, or there are these, they can find all kinds of beautiful, very stable, very periodic orbits. And for that, you require mathematics to keep creating a new set of periodic orbits. So classification of orbits, you must have heard of low Earth orbits, medium Earth orbits, high eccentricity orbits, and so on. So we have different satellites for different purposes, and they are put in different orbits. These low Earth orbits, they are located between 250 kilometers to 2000 kilometers above the Earth's surface. And since these are these low ones, they have to go very fast because the gravitational force of Earth is high, since the radius, the orbital radius is not much. So they go very fast. They go at almost at 7.8 kilometers per second. But as you go further, say from 250 to 200 kilometers, then the speeds can become slightly slower and slower and slower. So it becomes from 7.8 to 7.79 and finally 7.12 kilometers and so on. And you must have heard of the International Space Station. It is orbiting at 400 kilometers. And it orbits the Earth in 93 minutes, right? And the Hubble Space Telescope, HST, you must have heard of Hubble Space Telescope and must have seen the spectacular images which have come from the Hubble Space Telescope. This is at around 540 kilometers above Earth's this thing. And the orbital period is about 95.42 minutes, right? So as you go further and further off, since the gravitation force becomes weaker as you go, because gravity goes by 1 by r square, hence the velocity has to reduce. Otherwise, the centrifugal force will push the satellite out of the orbit. So to keep a satellite into the right orbit, you have to match the gravitation force with the centrifugal force. Orbits which go beyond 2000 kilometers, these are called the medium Earth orbits. And then you have the geosynchronous orbits. There are certain orbits, satellites, which they move in such a way that they are in synchrony with the Earth. They are specifically on a exact position on our Earth at a specific time, right? So this orbital period of these is same as the rotation period of the Earth. And these geostationary satellites are permanently fixed in exactly the same position in the sky as viewed from any fixed location on Earth. The satellites in these orbits are always tilted to an angle of about, which go from 0 to 90 degrees to the Earth's equatorial plane. Then you have the geostationary satellite, and this revolution, these geostationary satellites are in the equatorial plane of the Earth, and they are at about 36,000 kilometers, and their orbital period is exactly 24 hours, right? So they have to be at only at 36,000 kilometers. You can do a little bit of math calculations. School level mathematics will show you that from the center of the Earth, these geostationary orbits are at 36,000 kilometers. Then we have these high Earth orbits. These high Earth orbit is a geocentric orbit with an altitude greater than that of geosynchronous orbit, and the orbital periods of such orbits are greater than 24 hours. Hence, satellites in high orbits, they have an apparent retrograde motion. Okay, that is on Earth, you see that it is drifting, it is not rotating in synchrony with the Earth, but it appears that the Earth is rotating faster while this is going in the opposite direction. Yes, it's called the retrograde motion. So all these orbits, all these satellites, as you know, depending on what is the purpose, whether you want to monitor a specific location on Earth or whether you want to scan the whole Earth, you have to put them in different orbits. Because if suppose you want to scan Moon or Earth, you put it in orbit in the polar axis, and as the body rotates in the center, the satellite keeps moving in one fixed plane, and at the center, the body rotates, and time to time it scans the whole thing, right? Then there are different orbits like the Molniya orbits, Tundra orbits, and so on. So I will not get into the technicalities of this, but these are very highly eccentric orbits. They go very far, they hover above, come down very close. So close approaches are so on. Okay. So, so for any three bodies problem, we can find these Lagrangian points, which we had done it, which I had discussed earlier. And similarly, we can find it for the Sun, Earth in a satellite system. And we have L1, which is lying between Earth and the Sun. We have L2, which is lying beyond the Earth on the other side. L3 is beyond the Sun on this side. L4 and L5, they form equilateral triangles. So the distance from Sun to Earth is about 150 million kilometers. The distance from Sun to this L4 and from Earth to L4, these are also 150 million kilometers, 150 million kilometers. Similarly, L5 is the same. These form equilateral triangles, while the distance from Earth to L1 and Earth to L2 is approximately 1.2 million kilometers. And L1 is a good point where people have put a satellite which is called SOHO. It is Solar Heliocentric Observatory, which looks at the sun all the time and keeps monitoring the sun. It monitors the discharges which comes out. It studies the storms which can come and disrupt, and warns us that there is going to be a solar storm soon and so on, right? Interestingly, around these Lagrangian points, we can define orbits. So you see this is called a Lyapunov orbit, which is orbiting a Lagrangian point. And you notice that there is nothing sitting at the Lagrangian point, but you can find orbits, and a little bit of mathematics does that. You have equations of motion which we have got. You change the location, the center of mass to this point, and you get certain equations of motion, and you solve them, and you find that you can find orbits which are either which lie within in the same plane as the Earth-Sun system or Earth-Moon system in the XY plane, or you can have perpendicular to that, right? So these Lagrangian, these are the Lyapunov orbits. And in fact, not just one, you can have a class of a whole family of Lyapunov orbits, and at different heights, at different, we can do it. And you see on the right-hand side, the whole family of orbits which you can find. So what is being done now is, around these Lagrangian points, they are putting various satellites. For example, on one orbit, you have a Gaia satellite, and on the other, you have James Webb satellite. I'll discuss this as we go ahead. Other than that, there are orbits which are called the Lissaju orbits. Lissaju orbits include components in this plane and the plane of the two bodies, and also in the planes which are perpendicular. And they follow these Lissaju curves. And these Lissaju orbits are semi-periodic. These are not absolutely periodic. They are almost periodic ones. Lyapunov ones are always, they are perfectly periodic. While Lissaju, usually they are not absolutely periodic. They are semi-periodic ones. So these Lissaju orbits can be within the plane and out of the plane too. Okay, so another class of orbits we can define are the halo orbits, which are again periodic orbits like the Lyapunov orbits, and you can find around L1 and L2, and you can even incline these halo orbits. These are spherical orbits, so you can incline them at different angles to the L2 points, right? So these halo orbits again are very interesting points, and what is important for us is to see that how these orbits change when there is radiation pressure which comes in, or if the body is not spherically symmetric but oblate and so on. So utilization of the Lagrangian points, like I mentioned, you have between the sun and earth, we have L1, where we have a SOHO satellite sitting, which is monitoring the sun. And at L2, we have one Gaia satellite. And recently, this February, another satellite reached the L2 point of Earth-Sun system, which is called the James Webb telescope. Yeah, this is a telescope which will is the next one after the Hubble Space Telescope. Hubble Space Telescope was only a 2-meter telescope, while James Webb is a 6-meter class telescope. So these are orbiting the Lagrangian points, right? So you have orbits where, so when we have to go, we are living at a time where there's interplanetary mission. Already we have sent probes to moon. People have gone to moon all the way back in 1960s. But humans have managed to send missions to other planets, Voyager missions, Venera missions, Mangalyaan missions to Mars and so on. So the way that is done is, first they are put in a certain orbit, like they put in a low Earth orbit, and then you move it into an elliptical orbit by giving a thrust at a point, moving it to an elliptical orbit, and then again you change the orbital elements and you move it back into another orbit, and again the third. So there are different ways where you can transfer from one orbit to another. Either you can use a parabolic transfer orbit, or you can use a bielliptic transfer orbit, or you can use a Hoffman transfer orbits. In Hoffman transfer, you have from an inner circular to an outer circular one using one elliptical orbit. This is the Hoffman transfer orbit. But you have also bielliptic. So here you use two elliptic orbits to go from one circular orbit to another one. And you can calculate and see sometimes one bielliptic transfers are more fuel efficient, and sometimes Hoffman transfer orbits are more efficient. So depending on from which orbit you are sending it to which one, it makes the difference, right? And for all of this, I'm sure you can appreciate there's mathematics which is involved. This is just a slide to show you how the equations look like when we are looking at these halo orbits. And these are the equations which have been derived by my student, who again is a girl mathematician, Ibtisam. And she is looking at halo orbits around the Lagrangian points where there is radiation pressure also which comes in, and how the stability of these orbits change because of the photonic or the Poynting Robertson drag which comes in. And she's also taking into account oblateness of the Earth. So as you see, these factors Q, they give you the radiation terms, and your factors like rho and so on, these are giving us the oblateness parameters. So now coming to this point, I was giving you the mathematics of required in defining orbits and planning orbits. When you send people from Earth to Moon, or you send probes to these places, you have to have a lot of mathematicians who have to calculate the whole trajectory. They have to decide at what point the thrust motors have to be switched on, how to move it from a circular to an elliptical, and everything has to be exactly precise. Even the time of the launch has to be taken into account, because there are certain windows where you can launch a satellite. And if you miss that opportunity, sometimes you have to wait for weeks together or months together to find the next window, because the position of the moon would have changed, position of Mars would have changed. The perturbations which come in, the whole thing gets affected. So all these are done by mathematicians. And today we'll talk about the spectacular women who are behind very successful space programs. So I will give names of and works of three American pioneering women who worked. One is Katherine Johnson. Katherine Johnson, she began her career in 1953 at the National Advisory Committee for Aeronautics, NACA, which later in 1958 became NASA, National Aeronautical and Space Act of 1958, it moved all its operations from NACA to NASA. So she started her journey from NACA, and in 1957, she was among 3 women who were invited to NACA. That was that period when women were not allowed to be in these space programs, they were not allowed to do mathematics. But this lady, as from a very young age, she showed talent in mathematics, and she went all the way studying mathematics, geometry, analytical geometry, and so on. And she was a human computer. They were called to make calculations. So after going there, she spent her first year analyzing the data from flight tests and investigating a plane crash caused by the wake turbulence. And she used all this knowledge when she worked for Apollo missions and various other missions, which I'll just talk about. In 1957, with the success of Soviet satellite, right? You probably are aware that Russians were the first one to put a satellite which orbited the Earth, which was called Sputnik. And that started the space race between America and the USSR. And that's when people, all these brilliant people like Catherine Johnson and all were invited to look into it to make the American space program successful. She created a document which was a collection of lectures given by engineers who, along with Catherine Johnson, all these lectures, they became the core of the Space Task Force for the space travel program of the USA. In 1960, Catherine Johnson co-authored a report which is titled Determination of Azimuthal Angle at Burnout for placing a satellite over a selected Earth position. And this was the first time a woman in Flight Research Division had received credit as an author of a research paper, right? So she was, otherwise all the men were given credit. Even if women contributed, their contributions were never acknowledged. So this was the first time a woman, and this has been published. And in 1961, Catherine calculated the trajectory for Alan Shepard, the first American in space, entirely by hand. That was the time when computers were not there, or they were very primitive. So the whole calculations, she did it by hand. And his safe return also depended on Catherine's calculations. In 1962, even after NASA started using electronic computers, John Glenn, he was not confident with the computers and calculations. So he requested that Catherine should be called to check those calculations which have been made by computers, to check whether it is correct or not. And Catherine manually did all the calculations again, rechecked it, and only then this John Glenn, he sat in his aircraft and went, right? He became the first American to orbit the Earth. In 1969, the Apollo moon landing program, Catherine Johnson's calculations were critical to the success of Apollo moon landing, and not just landing, but successfully getting back the people from moon, right? In 1989, she continued to work until 1989 space station, when the space station was launched, and Catherine's calculations and her inputs were very essential for all the Apollo flights and so on. She has been awarded the Lunar Space and Operational Group Achievement Award, NASA Apollo Group Achievement Award. Then she received in 2015 Presidential Medal of Freedom. It's the highest civilian award which is given, and this Barack Obama presented to Catherine. So this is that seminal paper of Catherine, which I mentioned, and you see the computations which are on the right side, just a glimpse of the kind of computations she could do, the kind of expression she could solve, and see calculating the errors which would come in if you take oblateness into the picture and various things. The other names are Mary Jackson and Dorothy Jean Johnson Walk. Mary Jackson lived from 1921 to 2005. She was an American mathematician and aerospace engineer who worked in NACA and later NASA with Catherine. These three Black American women were called the human computers, who did all the calculations by hand. And they were the force behind successful space programs of the US. And Dorothy Jean Johnson Wong was an American mathematician and human computer who worked for this in NACA and later by NASA. And in 1949, she became the acting supervisor of the West Area Computers and the first American woman to receive a promotion and supervisor group of a staff in the center. So remember, these ladies were not only women who fought against those times, the times when women were not allowed in universities, but when time women were not allowed in research institutes and in universities or space programs. And they were brilliant women who fought for the rights of women, and they showed their talents. And on sheer merit and determination, they proved to the world that they are no less than the best men around. The story continues with the women of ISRO. India has a very successful space program. This is what I started off with. And I'll end with what I said. ISRO is one of the most successful government organizations. And we have an indigenous space program. We are among the league of 5 countries which have reached the moon, which have reached Mars. And India was the only country, the first country to reach Mars in the first attempt. US had many failures before they reached moon. Mars, similarly, Russians had many failures. Chinese had many failures before they had their successful missions. But Indians, they sent the Mangalyaan mission in one go, and they used the Hoffman transfer trajectories. They kept moving it in these elliptical orbits. At each time, slingshotted using gravity and used it. And finally, right, so there were about 500 scientists which were working for this Mangalyaan mission, working on the dynamics, the orbital dynamics of the whole thing, deciding then the payloads, deciding what experiments have to be done, creating, right? So a team of 500 scientists, from which 27% of them were women. 27 of them were women who were holding key executive positions, right? And here you see the picture of these ladies celebrating after the successful Mars mission. So this MOM, Mangalyaan Orbiter mission, was a calculation intensive mission. The navigation or mission aspects required a lot of iterative calculations. Through all maneuvers, designs and calculations, the women team stood by the decisions, and the accuracies were fabulous, right? And we salute to all these. And with this, I come to the end of my talk. Thank you. If there are any questions, I would be happy to answer them. Are there any questions? Hello, was I audible? Could you hear?
Yes, sir.
Yeah, okay. If there are no questions, then shall we close the session?
Thank you, sir, for readily accepting our invite in spite of your busy schedule and for such an informative lecture. Now
Thanks, sir. Thank you for giving
Thank you,
this
sir.
opportunity.
We are very fortunate to have here to listen to your lecture, sir.
I hope I could get my matter across. I hope, because there are no questions at all. So I'm wondering whether the students have understood or not. Could you hear me at all? Or
Sir, they might understand, sir. Then only that.
yeah, okay. But you have to encourage them to ask questions, because science grows only when you question.
Yes, sir.
The students have to learn to doubt what the teacher says and to question them all the time. That's how maths grows. That's how science grows.
Yes, sir.
Okay. Okay. Thank you.
Sir, for this small appreciation certificate for you, sir.
Thank you. Thanks a lot.
So please accept it. And I will be sending this to your mail, sir.
Thanks, sir. Thanks a lot. Thank you for giving me this opportunity. And thank you for your the certificate. Thanks a lot.
Welcome, sir. Now I call upon Prasanna to propose formal vote of thanks.
Thank you, madam. On behalf of the Mathematics and Statistics Department, it's my privilege to propose vote of thanks for this today's National Level FDP. First of all, I thank today's resource person, Professor Syed Nazimul Hassan, sir, Head Department of Mathematics, and was Dean at Maulana Azad National Urdu University. Sir, you explained very clearly and extremely well about orbital mechanics, orbital elements, and the classification of orbits. So how it will work, function mathematically, explain very well, sir. Thank you, sir. My sincere thanks to Professor K. Mucham Reddy, sir, Secretary, Hyderabad Mahila Vidya Sangam. I thank Professor G. Sudarshan Reddy, sir, Secretary cum Correspondent. I thank our Principal, Dr. J. Achita Devi ma'am, and I thank Head Department of Mathematics and Statistics, Shweta Srivastava ma'am, for organizing this today's National Level FDP program. I thank my dear colleagues and students for attending today's lecture. Thank you for giving me this opportunity. Thank you, one and all.
Thank you.
Thank you, Prasanna. Thank you, sir.
Thanks a lot.
I thank the participants also for patiently listening, and we will be again joining for the next session tomorrow at 3 p.m. by Mr. Alap Hassan sir on Emmy Noether's theorem. Thank you, one and all. Thank you.